Let me just first of all, though, say that usually we just skip over the first slide, but in this particular case, I just wanted to point out that over here is an artist's rendition of the New Horizons spacecraft as he perceived it to be coming in to visit Pluto and Charon, right down here. And this is a real image taken from the New Horizons spacecraft as we approached. One of the iconic views, now iconic views of Pluto and Charon in natural color. We'll see a lot more of this in a few minutes. And then down in the lower left, look at this, just incredible. After we flew by Pluto and looking back at the sun, and I'll say a lot more about this in a few minutes. So, we're on our way to talk about the New Horizons mission. Let me just, before I get into the results, so I just want to say a little bit in way of background so you'll understand the context of the mission. This is the initial reconnaissance of what we call the solar system's third zone. Now, what do I mean by that? If you think about the architecture of the solar system, we divide it into three regions. You have the terrestrial planet region, which is comprised of relatively small rocky planets, Mercury, Venus, Earth, and Mars. And then you go out into the second zone. You step a little bit farther out and you get into the region of the giant planets. Huge monster planets. Jupiter's 320 times as massive as the Earth, has this giant gaseous envelope around it. And then you go out to Saturn, Neptune, Uranus, and Neptune. In this little cartoon view of the solar system, our region, the terrestrial planet region, doesn't even rate. This is a big picture view of our solar system. But after you step beyond the giant planet region, you get into what we're now calling the third zone, that we didn't even know existed until the 1990s, called the Kuiper belt. And it's represented here in this cartoon fashion by these white dots. It's sort of a donut-shaped region surrounding the sun. Roughly, most of the objects are roughly in the same plane as all of the other planets. That's what we call the ecliptic plane. But they also go all over the place as well. Pluto's orbit is shown in yellow here. Okay, it's actually tilted by 19 degrees to that plane of the other planets, and it's also not circular, unlike the Earth's orbit, which is almost perfectly circular around the sun. Pluto actually travels inside of Neptune's orbit to about 29 astronomical units from the sun. You know, a convenient yardstick to use for the solar system dimensions is 1 AU. The average distance between the Earth and the sun is called 1 AU, 1 astronomical unit. Pluto right now is about 32 AU away from the sun. But it actually came within 29 AU inside of Neptune's orbit in 1989, and it's on its way out now, and it'll go all the way out to 48 AU. It's an elliptical orbit, very different from the other objects in the solar system. So the New Horizons mission is the first in situ reconnaissance of this newly discovered region in the solar system. This is the frontier of our solar system and the frontier of planetary science. And it turns out that this region is more populated than anywhere else within it, in the inner solar system. Okay? Most of the objects in the solar system are in this Kuiper belt region. And we want to see what they're like. They also tell us, because they're so far away from the sun, they've been kept cold most of the time since the time they formed 4.6 billion years ago. They've preserved better than almost anywhere else in the solar system what the conditions were like at the time of the formation of the solar system. And the discovery of the Kuiper belt and the three different classes of objects in the Kuiper belt, it turns out there are three families of objects in the Kuiper belt, really completely revolutionized our view of the solar system's formation and evolution. Most of us were taught that all of the planets, their current configurations, they've been there in that configuration forever. But it turns out that with the discovery of the Kuiper belt and the recognition of these different families of Kuiper belt objects, that we now realize that the solar system, the early solar system, went through this tumultuous period when there was a huge amount of what we call radial migration. The giant planets, Jupiter, actually came almost within Mars's orbit and then went back out again. And all of the other giant planets just came in and then back out. Uranus and Neptune, we think, actually switched places. This was all happening within the first few 100 million years of the solar system's existence. And all of that knowledge, the understanding of what was happening in the early solar system, was motivated by the discovery of the Kuiper belt and our understanding of the different objects in the Kuiper belt. But it is way the heck out there. You know, more than 30 times farther away from the sun than the Earth is. And it takes a lot of energy to send a spacecraft to the Kuiper belt. So in the case of the New Horizons mission, we had to get the biggest and baddest rocket that was available, the Atlas 5551. This is a picture of the rocket, 200 feet high. Our spacecraft is like a little hood ornament on the top of this giant, oops, let me go back, sorry about that. So 200 feet from this end to this end, 5 solid rocket boosters surrounding the core engine here, a Centaur second stage, and then even a third stage, this Boeing Star 48 third stage. Several million pounds of thrust to propel a 1,000-pound spacecraft out to Pluto. That was what was required, okay? And that's what we did. And I always like to show this. It takes me back January the 19th, 2006. 2 p.m. in the afternoon. The fastest spacecraft ever to leave the Earth. And still, it takes 9.5 years to get to Pluto, but it was leaving the Earth so fast, more than 30,000 miles per hour, it passed the orbit of the Moon in only 9 hours. So we took off at 2 p.m. I went out on our porch at 11 p.m., looked at the Moon. It was a full moon. The New Horizons spacecraft had already passed the orbit of the Moon. It took the Apollo astronauts 3 days. Okay? We actually passed by Jupiter in only 13 months, also a record. It took the Galileo spacecraft, the spacecraft that was dedicated to the study of Jupiter, 5 years to get there. Now, this is the, just a color-coded view of the path of the New Horizons spacecraft as it left the Earth. The Earth is down here, and color-coded by year, starting off with black and then purple and blue and so forth. Each year you can see where the spacecraft was as it's heading out, and you can see the relative configurations of all of the other objects in the solar system. Okay, so like I said, in late February of 2007 is when we passed Jupiter. Now, we actually directed the spacecraft near Jupiter in order to pick up a gravity assist from the incredible, Jupiter is so massive, like I said, 320 times as massive as the Earth. Well, we stole a little momentum from Jupiter as we passed by and increased our speed by 20% and cut more than 3 years off the travel time to Pluto. That was the primary purpose of flying near Jupiter. But in fact, we flew close enough that we got fantastic science as well. I don't have time to go into that, but we saw the most detailed view of the volcanoes on Io were mapped by the New Horizons mission. But anyway, as we stepped out, so in 2008, we passed by the orbit of Saturn. 2011, Uranus. Finally, in 2014, just a year before the flyby, we passed by Neptune. And finally, in July the 14th, 2015, so just this past summer, 7,800 miles above the surface of Pluto. This is the spacecraft. Once again, an artist's recreation of the spacecraft, very accurate though. Just to quickly show you the size of the spacecraft, 2.1 meters, so just a little under 7 feet across, about the size of a grand piano. We have a suite of very advanced instruments, the most advanced instruments to fly on a planetary spacecraft up until this point. We had the LORRI instrument, the Long-Range Reconnaissance Imager, built at APL. Those were our eagle eyes to get the highest resolution images. As we flew by Pluto, we got images that have a resolution about a football field size resolution at Pluto. Okay? If you were flying over New York City, at that same distance, you would be able to see the individual lakes in Central Park, And that's the kind of resolution that this instrument provided at Pluto. We had a color camera, infrared spectral imager that allows us to map the composition of all of the objects in the Pluto system. We had an ultraviolet spectrograph that was used to measure Pluto's atmosphere. We had a couple of particle instruments that measured the plasma in the vicinity of Pluto. And then we had, as part of the antenna system and the communication system, a radio experiment that allowed us to probe the temperature and the pressure in Pluto's atmosphere as we flew by, and I'll talk a little bit more about that in a minute. This is just showing you the actual instruments themselves, and I don't want you to have to go. I'm not going to go through each one of these instruments, but the point that I want to make, to you right now is down at the bottom, is summarized down at the bottom. What we needed to enable this mission was to have not only powerful instruments, but they had to be lightweight and very energy efficient. Okay? We could not fly giant solar panels out at Pluto. The sun is 1,000 times fainter at Pluto's distance than it is here at the Earth. So we carried a radioisotope thermoelectric generator to provide the power. So we were a nuclear-powered mission. But still, at the time of the flyby, we only had 200 watts total. All of those instruments together, turn them on all at the same time, they still draw less than 30 watts of power. So for less power than you're required for a light bulb in your house, you could run all of the instruments on the New Horizons mission. And they weighed less than 70 pounds altogether. The weight of all of these instruments was actually less than the single camera on the Cassini mission. Okay? But we needed that because we had to be as lightweight and as energy as possible to be able to even enable this mission to go all the way out to Pluto. Okay, so let me just remind you about the Pluto system. As Frank was saying earlier, Max Muschler and I and other people on the New Horizons team, when the mission was selected back in 2001, we only knew about Pluto and Charon. That was, and the mission was already approved to go to those two objects. But at that point, we realized, well, we're going to go there. We should take inventory of what's really around Pluto. We used the Hubble Space Telescope in 2005 and discovered two new little moons, Nix and Hydra. Hydra here, Nix here. And then a few years later, in 2011, 2012, we found two more little moons, Styx and Kerberos. So we lucked out here. 6 for the price of 2. Okay, this is the deepest picture ever taken of the Pluto system with Hubble. And we could just barely see Styx in this image. Over 100 minutes with this very powerful WIF-3 camera, and we could barely make out Styx. This was a fantastic technical achievement. Okay, but we're actually going to go there, so we can say a lot more. As far as the scientific objectives of the mission, don't worry about reading all of this. The most important scientific objectives of the mission can be summarized by 3 phrases. And those are highlighted at the very top here. Basically, what does Pluto and Charon look like, and all the other objects in the Pluto system look like? Okay. What's the composition of Pluto and Charon's surface? Okay, we want to map the surface composition. And then finally, the third major objective of the mission is to characterize Pluto's atmosphere. So that's what we were after. And these were put together by consensus in the scientific community. Now, we like to call 2015 the year of Pluto. We actually started observing Pluto with New Horizons way back in January. We had approach phase 1, approach phase 2, approach phase 3, and then our departure phases. But really, most of the action, all of the best results come within plus or minus a day of that time of closest approach on July the 14th. That's where most of the action was. That's this purple region here. All of these objectives were accomplished during those couple of days. Okay, now, that's just for background. Now let's just talk about some of the exciting results. Okay, so this is the best that we could do prior to the New Horizons mission. This is a Hubble image taken in 1992. It's a pixelated blob, right? But you can see, this is an amazing technical achievement. You can actually, Pluto's 3 billion miles away. it's only about 1,500 miles across. And from that great distance, you can still make out bright and dark patches on Pluto's surface. But look what happens when you actually go there. This is the iconic view. This is the lesson of 50 years of space exploration. If you really want to make this huge leap in your understanding of a system, of planets, planetary objects, you have to go there. And it turns out, just by coincidence, at the time of the closest approach, July the 14th, 2015, exactly 50 years to the day that Mariner flew by Mars in the very first planetary encounter of an extraterrestrial planet. And that's just a cool fact. Okay, so this is the iconic view we now have of Pluto. You see the so-called heart of Pluto. This region here, which we call Tombaugh Regio, named after the discoverer of Pluto, Clyde Tombaugh, an American astronomer. This is a giant sheet of a very exotic ices, molecular nitrogen, carbon monoxide, and methane. Okay, just a sheet of ice, a giant glacier, basically, 1,000 miles across. Okay, you have this incredibly bright area, reflecting about 70 to 80% of the sunlight off of it, and then around the equator. By the way, the pole is here. This is the equator. It runs like this. The geometry is very funny. Pluto's tilted over, but the equator is running along this region. Right next to, let me just bring this. By the way, this is natural color. This is our best representation of what we think your eye would see if you were there on the spacecraft flying by Pluto. Okay? Just a huge variation in brightness between about 70% reflectivity here down to about 10% down here. Okay? And that's because, unlike this region, which is just covered with ice, this is a region that we think is primarily comprised of complex hydrocarbons. Okay? What we call tholins are coating the surface of Pluto in this region. If instead of trying to make Pluto look like what your eye would see, instead of doing that, if you instead take the different color filters and stretch them so that you emphasize the differences, you get a picture like this, in which you now see the heart actually breaks into two ventricles, two very different ventricles. They have different colors, and that's telling you something about the compositional differences that are being displayed across the face of Pluto here. You see this sort of a light brownish mix at the top. You see the very dark reddish region of complex hydrocarbons down here, and this very bright icy region right there. And then you can do things like putting it on the globe and just rotating it around. Now, Pluto takes 6.4 days to rotate completely around, but we're flying by at 30,000 miles an hour. We only get a great view of one side of Pluto. Okay? And that's this region here. This, of course, so what we did here was take the globe, and then turn it into a map, just like what you see for the Earth. Okay? So the region that we map at high resolution is shown here, and this really doesn't do it justice. Really, I recommend that you all go to our website and download these images, which are available to the public, blow them up, and then roam around, just to be amazed. There's so much detail in these images. But this is the region of Pluto the face of Pluto that we see very well with the New Horizons mission. And we've already started naming informally. These won't be accepted, for a couple of years. It takes a long time to go through the naming process. But as I said before, the heart of Pluto we're calling Tombaugh Regio, and you can see, we name various other areas after spacecraft, for example, Voyager, Venera, Pioneer, so forth and so on, and then we have craters named after individual people. But you can see the region that the other side of Pluto that we don't see as well as high resolution, but we still see dramatically better than we could from any Earth-based platform. Okay, now, just to orient you a little bit, let's fly over the that region of Tombaugh Regio called Sputnik Planum. Okay? So we're going to fly over that using actual images from the New Horizons spacecraft, starting down here and then working our way around. Okay, this is just look at the landscape. You know, this is as if you're flying. These are actual images, though, taken by the New Horizons spacecraft. We just passed over the mountain range, and now this is a region of what we call chaos region, and then up until the northern edge of Sputnik Planum, and then just swinging back around to give you the view of the whole planet. Okay, now what I'd like to do is once again put up the whole face of Sputnik Planum, and now just highlight. Highlight about 6 different regions to focus in on. Because, like I say, just looking at the whole globe, you can't really appreciate the detail that we're seeing by from the images that we took during the closest approach. So we're going to look at something that we call we have mountain ranges down in this region of Sputnik Planum. We have a couple of isolated mountains down here. This is actually our highest resolution images that you'll see in just a few minutes right there. This is the region where there's chaos. We have glacier flow up here and then what we call snake skin here. So let's just walk through those and show you some of the detail that we get. Okay? So that giant ice sheet is actually moving just like the glaciers do on the Earth. And the evidence for that is these little swirly things. You see where there are barriers, you see what appears to be flow lines of the ice. This is very soft molecular nitrogen ice flowing around barriers as we head into the highlands area above Sputnik Planum. And then you see it reaching the upper highlands area here. And for scale, you can see 20 miles down here. And look at all these weird structures. Okay, this is just another example, except that instead of flowing out of Sputnik Planum into the highlands, we have it flowing the other way. What we think is happening in this case is this pitted terrain over here. We have the ices sublimating from this region, in other words, evaporating from the surface, condensing back into this region, and then finally that ice is now flowing back downhill back into Sputnik Planum. So you have this transport of material from here over to here and then back again, flowing through these channels. Okay, so this is a channel just a couple of miles across. And if you look at it from a completely different kind of angle, that was a high sun where the sun was almost like at noon, as opposed to looking at it at a very large angle. You can see the flow lines even better. Okay, so these are channels that are channeling that ice coming down from a high region down to a lower region. Okay, we have mountain ranges on Pluto's surface. We have the Norgay Montes over here, this mountain range. These are about 11,000 feet high, so approximately the height of the Rocky Mountains in the United States. And then the Hillary Montes over here are about the size of the Appalachians. Okay, you get these are, what these are? These are actually giant icebergs sticking out of the crust of Pluto. Water ice. Pluto is so cold, the temperature at the surface is like minus 390 degrees Fahrenheit, approximately, on the surface. So water ice isn't like water ice that you have in your freezer at home. It's like a rock. Okay? But that rock is, as you know, water ice becomes less dense when you freeze it. It's actually sticking up out of the crust and floating on this molecular nitrogen ice. Now you go to another region up along the western side of Sputnik Planum, and look at these things. And here's the scale, 50 miles. You've got just a mess of giant boulders. These are icebergs, essentially. Once again, water icebergs, we think, probably being lifted up from the crust. There's upwelling and downwelling, happening in the crust of Pluto, we think. Okay? There are planetary processes, tectonic-like processes taking place that are producing these kinds of things. It turns out that on Europa, one of the Galilean moons of Jupiter, the one that we're planning a mission to now that we think might harbor life, this giant oceans under the surface, also has a region that looks very much like this, although smaller scale. The icebergs aren't as big on Europa as they are here on Pluto's surface. Now look at this. This was just blowing us away. What the heck is this? I mean, we've called this the snakeskin region, these linear features and ponds of ice probably over here. These are ridges. These are called dorsa, but they're almost unlike anything else that we've seen in the solar system. This is Pluto's surface. And then this is one of the highest resolution images that we have down. This is right in the middle of Sputnik Planum in that white sheet, white area, which is highly reflective, except there are a couple of isolated mountains right in the middle of that, and they're seen here. And just look at the surface, the detail of the surface. I mean, this is an object that's 3 billion miles away that we had only this pixelated view. We basically transformed Pluto from a pixelated blob into this complex, diverse world, right? We've gone from planetary astronomy to planetary geology. The mission has taken us there. Now, just a couple of weeks ago, this is one of the images that came down. I'm sitting at my computer just getting blown away by stuff like this. This is Pluto about 5 minutes after the time of closest approach. So the sun is behind us, okay? The sunlight is coming from directly into the screen here. Look at this. We're seeing not only this incredible surface of Pluto, but a haze. There's a structured haze of particles in Pluto's atmosphere. Okay? This was a surprise to us. But look at this view. And now if you zoom in a little bit, I felt like I was there. Just roaming around. These are, like I say, this is the Norgay Montes, the Norgay Mountains. So these are about the size of the Rocky Mountains. But you see the sun is coming from there. You see the shadows. This is how we tell the size, by the way. We measure the length of the shadows. The sun is coming in, shining in. You see the shadows. We also have stereoscopic views of Pluto. But we're just in the process of getting. We're just getting those down now, and in the process of putting those together. But it's stuff like this, and this is Sputnik Planum once again, viewed from this very low sun angle. It looks very different. Okay, now switch gears, go from Pluto to Charon. Charon is pretty complex as well. This is a flyover movie. Look at Charon. All kinds of stuff on its surface as well. Canyons, deeper and wider and longer, much longer than the Grand Canyon in the United States on Charon's surface. A mountain in a moat. You'll see more about, we'll see that in more detail in a second. And here's our little annotated map of Charon. You can notice the Star Wars themes that we're using here, Vulcan, Planum, Star Trek, I meant. This is a color-enhanced view of Charon. Unbelievable. Look at it. It looks like it's been almost like split across the middle. There's this huge gash in Charon's surface that runs from one end to the other and all the way around. Okay? That's one distinguishing characteristic of Charon, but also the North Polar region has this dark material. It's like a hood of dark material. Where the heck is that coming from? Our best hypothesis for where this is coming from, you notice it's red and dark, just like some of the material on Pluto. We're thinking that maybe some of the material from Pluto's surface actually got transferred over to Charon, and in the coldest regions up in this northern pole, condensed onto the surface and formed this residue. Okay? These are, by the way, we're just getting these results now. Some of the things that I say may turn out to be wrong. Hopefully not. We've actually had lots of discussions of these things among our team, but we're just in the infancy of analyzing these data. we actually took, in addition to the color image, we took a swath across with our high-resolution camera of the LORI instrument across here, and then draped the colors from the color camera over that, an even higher detail. And here is that's a mountain in a moat right here. So you got a couple of kilometer deep, about a mile deep, moat, and sitting inside that is a giant ice mountain. Okay, the diversity in the Pluto system has just been mind-boggling to us. These are the two largest worlds in that system, Pluto and Charon. They're shown with exactly the same color scheme, okay? So, and they're shown at their observed brightnesses. So this is a true comparison of one object to the other, and look how different they are, okay? So Pluto, has all of this color variation, huge differences in brightness across the surface. Charon is a more muted, grayer object, okay? But it does have this region. This is why we're thinking that maybe some of this material eventually made it onto Charon. But they're two very different worlds. Just the diversity that we got from the New Horizons mission has been amazing. And like I said, we had no idea what to expect going into this, okay? Because there'd been no reconnaissance of this third zone in the solar system. So this is it. Okay, so in addition, we've actually been able to resolve those small satellites, the newly discovered satellites that we found with Hubble. Instead of little pinpoints of light that you can barely see, we now see them as resolved objects. Of course, they're tiny, so you don't have the kind of resolution that you have on Pluto. But this is Nix. Nix and Hydra, approximately the same size. Okay. These are three different views on approach, just before approach, and then after we pass by and just look at the little crescent of Nix. Well, there's a giant crater in the middle of Nix. And it's colored. It's colored differently than the rest of the object. What does that mean? There must have been an impact occurring, and maybe it excavated down in the interior might be different composition than the surface. I mean, that's our best guess at right now. And look at Hydra. Looks a little bit like Comet Churyumov Gerasimenko, the rubber ducky comet. You get almost like a double-lobed thing, plus a big chunk taken out here and a chunk taken out here. These things have been battered over the age of the solar system, 4.6 billion years, by meteoritic impacts, and they're rotating, and this thing is rotating really, really fast, probably because it's been impacted. Just quickly, these results are just coming in. Like I said, we had this infrared spectral imager, which is mapping the composition of Pluto and Charon and the small satellites. We only have about half of Pluto's surface mapped right now, but the pink is telling you where there's strong methane ice absorption, and where it's black is where there's hardly any methane. So we get a lot of methane in Sputnik Planum region, but hardly any here. And that's because that methane that was probably there originally has been bombarded by cosmic rays, charged particles, breaking up the bonds, turning it into more complex hydrocarbons that are redder and darker. That's what we think is happening. And now, just to quickly end up with some atmospheric results here, we had a really cool experiment on New Horizons. This shows you this red line here is the trajectory of the spacecraft through the system. So this is the Pluto system. And this is what I was telling you earlier about how the system is like tilted over. Pluto's pole is tilted way over, even underneath the ecliptic plane. This is the plane that contains Jupiter and the Earth and the Sun and all the other planets. So we're flying by. The Sun is in this direction, way off to the right. And so this is the shadow cast by Pluto. One of our mission design requirements was to fly the spacecraft right through the center of that shadow, because we had two experiments in mind. Using the ultraviolet spectrograph, as the New Horizons spacecraft went into the shadow, the ultraviolet spectrograph would be looking back at the Sun, and as the spacecraft passed into Pluto's shadow, it'd be looking at the absorption of sunlight in Pluto's upper atmosphere. And by breaking the light up into its ultraviolet wavelengths, you can actually see the signatures of the molecules in Pluto's upper atmosphere. Okay, very characteristic signatures of hydrocarbons, molecular nitrogen, and other species. Okay, that's what we were looking for in the upper atmosphere. But in addition, we had 2 experiments. The other experiment was to use the radio experiment. We had the deep space antennas on the Earth. These are giant 70-meter antennas. One's in Canberra, one's in Goldstone, California. So over 200 feet across, radiating 80 kilowatts of power up to the spacecraft. Those radio waves are passing through Pluto's lower atmosphere and being bent. The radio waves are actually, they change phase as they pass through the atmosphere, and the amount that they change depends on the pressure and the temperature of the lower atmosphere. Okay? And that was the second experiment. And we used both of those experiments to help us to characterize Pluto's very tenuous atmosphere. The atmosphere on Pluto near the surface is about 100,000 times less dense than what it is here in our room. Okay? So it's a very tenuous atmosphere, but coincidentally, it's also made primarily of molecular nitrogen, just like the molecular nitrogen in our room here is about 72% or so, but on Pluto it's more like 90%. Okay, so this is the kind of signal that you get as we flew the spacecraft. So the ultraviolet spectrograph is looking at the sun, and it sees a signal up here, and then all of a sudden, as we pass into the shadow, it starts to drop. But you see, there's not a nice clean drop. It's actually bent, and that's because it has an atmosphere. Pluto has an atmosphere. If you compare it to what happened when we flew by Charon, you see how much sharper it is, and that's because Charon doesn't have an atmosphere. Well, we're still looking, but at very, very faint levels. It's at least 3 orders of magnitude, a factor of 1,000 less. Okay, so we passed by Pluto, took all these wonderful pictures, but that wasn't the end of the show. I mean, we kept looking at Pluto as we passed by and looked back at Pluto, just a little crescent of Pluto, as the sun was shining through it, and we were surprised because this is where the sunlight is hitting the surface of Pluto. You see this little crescent here, but you see this light all the way around. And that's because Pluto has this haze. The atmospheric haze, there are particles in Pluto's atmosphere that we're seeing scattering of sunlight from. Okay? So Pluto has weather. There are actually a bunch of different layers in Pluto's atmosphere. And we're in the process of trying to understand what the composition of those particles are, how big they are. Those are things that we're working on now. And we actually could see, those little dark lines here. These are the shadows of sun rays coming through. The sun is shining through the atmosphere, and the places where there's a haze, a fog, you don't, you see, the mountain. The mountains are blocking some of it. Okay. Okay, so, all right, so, that brings me to the end of showing you the results from the Pluto mission. Things couldn't have gone better, for that week surrounding closest approach. It was wonderful. But there was some drama, during this mission. Just 10 days before closest approach, July the 4th, we had a scare. Okay? I was actually sitting in my office at home, working on New Horizons data, and I got a frantic call from the principal investigator, Alan Stern. He was clearly out of breath. He had been running. He said, "We've lost communication with the spacecraft." This is 3 billion miles away, 10 days from closest approach, after 9.5 years. Immediately, we're hoping that something has gone wrong with the ground station. It's not something wrong with the spacecraft, but so he came. I said, "Okay, I'll be there in 20 minutes." I had to leave my house. We were supposed to go to a barbecue that night. It's 4th of July, but they had to send my wife and not me. But anyway, it turns out that the spacecraft had left its 3-axis normal operation mode and had gone into safe mode. This is what was supposed to have happened. Okay, we were supposed to be in this 3-axis mode, and then on July the 7th, that following Tuesday, we were supposed to transition into this special encounter mode where, damn the torpedoes, if anything went wrong with the spacecraft, it was just going to autonomously try to recover put itself back on its observing timeline and just fly through any problems, okay? But we had to get to that point on Tuesday, and this is Saturday, the Saturday before, okay? We had spent 2 years putting together that sequence. It's a 9-day sequence, P minus 7 days to P plus 2 days, filling every second with science observations as much as possible, squeezing as much as we could out. And here we are, just a few days out from entering that course, and we'd stuffed it to the max. I mean, really, we did not want to go in and play with that sequence anymore. We had tested it on the spacecraft. We had already run a rehearsal, okay, and it run perfectly on the spacecraft back in 2013, okay? So we wanted to recover from this fault before we had to engage this what we call the core load. So here's what happened. We went into the safe mode on July the 4th. We exited the next day. People were working around the clock, and just about just a few hours before we were supposed to engage that core load, we actually did get back to square one. We got back to the baseline. And that was testimony to our our observing team, our mission operations team, and the head of that is called the MOM, the Mission Operations Manager, Alice Bowman, down here at the bottom. She had a cot, and actually an inflatable mattress that she had in her office that she was just running around the clock, but she knew that there was no way she was going to let this mission fail. And fortunately, within a couple of hours of us engaging the core load, we sent down the first images, and these are the first images. Okay, we knew everything was fine. We executed properly that observation. This is Pluto and Charon, and we were on our way. And then there was not a single thing that went wrong after that. The night of the encounter is when we get our first engineering data telling us how things went. We just get a little bit of data. And the thing that I was listening out for was how the autonomy system, if there were any flags that were set indicating that something had gone wrong. Not a single autonomy flag had been set. Everything just ran cleanly. Also, the control and data handling system engineer said he could tell from the telemetry that all the data had properly been transferred from the instruments to the solid-state recorders. So, we knew that the data had been captured. And at that point, we knew that we had a successful mission. And now is really just starting Labor Day weekend, we've started sending back the data. We're so far away, and we only have this 2.1 meter antenna. We have this very sophisticated transmitter, but being so far away, we can only send the data back at a maximum rate of 2 kilobits per second, so 2,000 bits per second. So unfortunately, it takes a fairly long time to send these images back. So we're going to be doing this for the next year, but the good part of that is that it's been like going to a toy store. This is a candy shop. Every day, I mean, as we speak now, we have passes every few days, for several hours each day. We're sending down these data. I come into my office, turn on the computer, and look at the images, and it's just, unbelievable. And, people's jaws are dropping to the floor. It's just been amazing. The big surprise of the mission so far has been the complexity and the diversity of the objects in the Pluto system. We had no idea that these dwarf planets, is Pluto a planet or what? The planetary processes that are taking place, we don't have an explanation for why they're happening yet. But that's what we'll be working on. We'll have to try and explain it. Presumably, Pluto isn't alone. There are a handful of other objects that are close to the size of Pluto in the Kuiper belt, and probably similar processes are taking place there. Let me just mention, this is my last slide. In fact, we're already 7/10 of an AU past Pluto. So the distance from Venus to the Sun is how far we're away from Pluto already. We're still traveling over 30,000 miles per hour. So we're heading deeper into the Kuiper belt. In fact, we'll be passing through the densest part of the Kuiper belt in a few years from now. And it turns out we have found an object that we can also fly, that we could fly the spacecraft by. We had to use Hubble. Hubble rescued the extended mission for New Horizons. If NASA approves the extended mission, we had to find a Kuiper belt object that was nearly along the trajectory of the New Horizons mission, the New Horizons spacecraft. We had a limited amount of fuel to change that trajectory, Okay, we could only change it by plus or minus 1 degree. Okay, so you imagine a cone in space, along the trajectory. We had to find an object that was somewhere in that volume of space, and that was no easy task. We tried for several years with the biggest ground-based telescopes, and were not successful. But Hubble came through last summer. We discovered a handful of objects, including what we call PT1. There were several people in the audience, by the way, who helped work on this. But it turns out that this object, PT1, which is officially known as 2014 MU69, a relatively small object, we think on the order of 30 or 40 kilometers in diameter. But we're going to be doing a burn on the spacecraft, a trajectory maneuver correction, in later this month and in early November that will set us on a path that will send us near that object. And we'll write a proposal to NASA next spring, making the case, the scientific case, for conducting a flyby. And if NASA approves, then that's what we'll be doing on January the 1st, 2019. We already know that's the day of closest approach to that object. But we need the support, of NASA to do that. We'll put in the proposal. Everything is working beautifully, so we hope that they're going to, accept this. And it turns out that object is a Kuiper belt object also, like Pluto is, but it's in one of those other. There are 3 families of Kuiper belt objects. It's in one of what we call the cold classical Kuiper belt objects. Pluto is in a resonance with Neptune. It's a so-called resonant Kuiper belt object. Could be very different from the cold classicals. The cold classicals, we think, are objects that probably formed in place where they are and have stayed there for their entire 4.6 billion years, relatively undisturbed, and may be more representative of the most pristine material in the outer solar system. So we're looking forward to that. And with that, I'll by the way, please, go to our website, pluto.jhuapl.edu. We have new results coming in every day. Every week we've been having a new release. And so if you want to keep up with what's going on, go there and download some of the images and play around yourselves. Thank you very much.